In frontier days, the blacksmith manufactured tools and other products from raw iron. Each piece he made, although similar to others, was one of a kind. Replacement parts were made to order. With the arrival of mass production, the need for interchangeable parts became much more important. Each part had to be manufactured to precise specifications. Today's products have even more demanding specifications. They require a whole new language for communicating design requirements. That language is geometric dimensioning and tolerancing, or GD&T. A language is made up of symbols. Some symbols are universal. They're recognized and understood by people throughout the world. GD&T is a technical drawing language whose symbols are recognized and understood by engineering, production, and inspection personnel worldwide. The symbols appear on the drawing in a box called the feature control frame. Only a few symbols are needed to communicate the design requirements for a part feature. The use of these symbols ensures that drawings are interpreted in the same way by everyone. GD&T is more than a system of shorthand, however. It's a means of specifying design requirements with respect to the actual function or relationship of part features. It helps design engineers to more clearly convey their design intent to production and inspection groups. In turn, those groups can develop the most appropriate machining, fixturing, and inspection techniques. GD&T was first introduced in 1957 by the American National Standard Institute. Since then, it's been revised several times to improve and update the dimensioning and tolerancing practices in the United States. Why has GD&T become so important to American industry and to industry around the world? First and foremost, it saves money by allowing maximum production tolerances. The result? Increased productivity. It guarantees the fit of mating parts by considering their functional relationship during the design stage. The result? Better product quality. It establishes a common engineering language, not only within the United States, but internationally as well. Technical drawings are interpreted the same way by everyone who reads them. Not only do people within a company speak the same language, people around the world will too. As a result, companies can more easily manufacture and sell their products in world markets. Why should GD&T be important to you? GD&T is fast becoming the standard language throughout U.S. industry, the military, and international business. Knowing how to interpret geometric dimensioning and tolerancing symbols is a necessary skill for anyone who must read a blueprint. This program will introduce you to basic GD&T terms, concepts, and symbols so that you can read and interpret drawings. Many will be familiar to you. Others may be new. Before we get into the GD&T symbols, you'll need to understand some basic terms and concepts. We'll use these model parts to demonstrate our explanations. Physical portions of the part, such as this flat surface, this hole, or this inclined surface, are called features. Features are defined by their dimensions. There are two types of dimensions, size and location. A dimension of size tells you how large a feature is. This hole, for example, is 1 inch in diameter. Dimensions of location tell you where the feature is located on the part with respect to other features. The hole is 2 and 625 ten-thousandths from the edge. Features are also defined by their geometric characteristics. Geometric characteristics define the form of the feature and its location with respect to other features. Flatness, circularity, perpendicularity, and parallelism are all examples of geometric characteristics. Ideally, each feature will be identical from part to part. Due to many factors, however, the features may vary. The amount of acceptable variation in the feature is defined by a tolerance. Dimensions of size and location are both allowed to vary by a tolerance. Geometric characteristics are also allowed to vary by a geometric tolerance. A geometric tolerance states how much the geometric characteristic of a feature may vary from the ideal geometric characteristic represented on the drawing. We'll talk about geometric tolerances later in this series. A tolerance takes into account the function of the feature and its relationship to other features in the completed product or assembly. For example, for an internal feature such as this hole, the upper tolerance limit is 753 thousandths, and the lower tolerance limit is 750 thousandths. For an external feature like this shaft, the upper tolerance limit is 747 thousandths, and the lower tolerance limit is 744 thousandths. The two parts were designed to fit together without interference, since the largest shaft will easily fit into the smallest hole. The difference between the largest shaft and the smallest hole is called the allowance. The allowance in this assembly is 3 thousandths. When an external feature like the shaft is at its upper tolerance limit, it is said to be in its maximum material condition, abbreviated MMC. Here the shaft measures 747 thousandths. It's in its maximum material condition. An internal feature like the hole is in its maximum material condition when it's at its lower tolerance limit. The hole measures 750 thousandths. It's in its maximum material condition. Another way to think of it is that a feature in its maximum material condition would weigh the most. On a drawing, maximum material condition is signified by this symbol. The opposite of maximum material condition is least material condition, or LMC. This occurs when an external feature like the shaft is at its lower tolerance limit, and an internal feature like the hole is at its upper tolerance limit. In its least material condition, the shaft measures 744 thousandths. The hole in its least material condition measures 753 thousandths. A feature in its least material condition would weigh the least. On a drawing, least material condition is signified by this symbol. The material condition of the two features affects how they fit together. For example, here the maximum material condition of the shaft is 496 thousandths. The maximum material condition of the hole is 500 thousandths. This is a worst-case condition, since the shaft is at its largest and the hole is at its smallest. If we subtract the MMC shaft from the MMC hole, the allowance is 4 thousandths. Since there is clearance between the two features, even in this worst-case condition, it's called a clearance fit. When two features have no clearance in their maximum material condition, but do have clearance at some point as they approach their least material condition, we have a transition fit. For example, in their maximum material condition, the hole is 500 thousandths, and the shaft is 502 thousandths. The allowance is negative, meaning there is no clearance between them. As a result, the two parts would need special equipment, like this arbor press, for proper assembly. Now let's see what happens as the two features approach their least material condition. In their least material condition, the hole is 505 thousandths, and the shaft is 497 thousandths. Now there's an allowance of 8 thousandths between them. There's been a transition from a force fit to a sliding fit. For some applications, a transition fit is necessary for proper functioning of the part. When there is no allowance between features, regardless of whether they're in their maximum or least material condition, they have an interference fit. The shaft cannot be inserted into the hole unless a special assembly method is used. Although it would seem that this is an undesirable situation, there are in fact applications that require an interference fit. For example, the assembly of a train wheel onto its axle. Both the wheel and the shaft are machined to dimensions that produce an interference fit. The wheel is heated, causing the metal to expand and increase the size of the hole. The axle is chilled, causing it to shrink to a size that produces a clearance fit, permitting the axle to be assembled with the wheel. Once the assembly returns to a normal temperature, the wheel and axle go back to their machined dimensions, producing an extremely tight fit. Let's briefly review the terms and concepts covered so far. Part features are defined by dimensions of size and location and by geometric characteristics. Dimensions of size tell how large a feature is, while dimensions of location tell where the feature is located with respect to other features. Geometric characteristics define both the form and location of a feature as well as its relationship to other features. These dimensions and geometric characteristics are allowed to vary by a tolerance based on the feature's function and its relationship to other features. An external feature at its upper tolerance limit and an internal feature at its lower tolerance limit are said to be in their maximum material condition. When the external feature is at its lower tolerance limit and the internal feature is at its upper tolerance limit, they are in their least material condition. The material condition of two mating features will determine whether they have a clearance fit, transition fit, or interference fit. With a clearance fit, mating features can be assembled regardless of their material condition. In a transition fit, features have no clearance in their maximum material condition, but do have clearance as they approach their least material condition. With an interference fit, there is no clearance between mating features regardless of their material condition. Open your application guide to Unit 1, Review Number 1. After completing the review, check your answers. If necessary, review the first part of this tape before proceeding. Now, let's take a look at two concepts of geometric dimensioning and tolerancing: basic dimensions and datums. A basic dimension is a number which describes the theoretically exact size, shape, or location of a feature. It's the basis from which permissible variations are established by tolerances on other dimensions in notes or in feature control frames. A basic dimension is identified by the box around it. Here, for example, the basic dimensions specify the location of the hole. At first glance, it appears that these basic dimensions have no tolerances associated with them. They simply state that the hole is theoretically 875 thousandths away from the top edge, and 2 62 thousandths from the right edge of the piece. A basic dimension always has a tolerance associated with it, however. Below the size dimension for the hole is a feature control frame which contains a tolerance for the basic dimension. It states that the location of the hole may vary by 2 thousandths. Another important GD&T concept is the datum. A datum is a theoretically exact point, axis, or plane from which the location or geometric characteristics of a part feature are measured. In other words, it's a starting place or origin. A datum is established from an actual part feature. The actual part feature is called a datum feature. This flat surface is an example of a datum feature. Magnified, you can see that the surface of a datum feature is irregular and imperfect. It would not serve as an accurate origin for measurement. Machine tooling and inspection surfaces, on the other hand, are considered to be perfect or exact. When in contact with a datum feature, they create a simulated datum plane from which more accurate measurements can be made. Usually, the largest and most important surface or feature that affects the part's function is used to establish the primary datum. There must be 3 or more points of contact between the part surface or feature and the machine tooling or inspection surface in order to establish the primary datum. Often, more than one datum is needed to accurately locate all the features on a part. So, secondary and tertiary datums must be established from other surfaces or features that are considered important to the part's function. At least 2 points of contact are needed to establish the secondary datum, while at least 1 point of contact is needed to establish the tertiary or third datum. Each of the 3 datum planes is perpendicular to the others. Together, they form the datum reference frame. The datum reference frame provides an origin from which measurements are made. The datum reference frame duplicates the 3 planes formed by the X, Y, Z axes on many machines, and the 3 planes used for common inspection procedures. For a cylindrical feature, the intersection of the datum planes establishes a datum axis. The addition of a third datum plane completes the datum reference frame. This is the symbol for a datum feature. Any letter except I, O, and Q can be used to identify the datum surface or feature. Double letters such as AA can be used when single letters are exhausted. The datum feature symbol usually appears on an extension line or a leader that extends from the datum feature. Here, the surface of the cylinder is the datum feature. When the datum feature is a feature of size, the placement of the datum feature symbol will vary. For example, here the datum feature symbol refers to the diameter of the part. Establishing datums on special parts like castings, sheet metal, and those with irregular shapes requires the use of datum targets. A datum target is a specified point, line, or area on a part. It represents a place of contact between the datum feature and the inspection equipment or tooling. Datum targets are used to establish the datum reference frame. They ensure that an irregularly shaped part will be located the same way during production and inspection.